Hello everyone, thanks for coming. Today I'm going to talk about deterministic ISSU qualification. What is ISSU? ISSU lets network switches upgrade without dropping a single packet. The application running underneath is none the wiser that an upgrade even happened. In Sonic, we also refer to this as warm upgrade or warm reboot. And then what is ISSU qualification? That is the process of assessing the warm upgrade that took place against a series of criteria and metrics. And it must pass all of these to consider the upgrade a success. Some implementations of ISSU, they use hardware to do this. This often involves extra redundancy, and as a result it costs a bit more. But in Sonic, this is fully software based. I'm not going to go into the details of how that works today, but if you're interested, feel free to head to this link here from Gohan, who presented this about 6 years ago at a past OCP event. Some challenges with ISSU qualification. We need to enforce that the LACP downtime across the warm upgrade is less than 150 seconds. If it exceeds this, we'll see some lag flaps, which will lead to data plane impact. We also need to ensure that the BGP sessions are restored within 240 seconds. Otherwise, the routes will be removed. Once again, we'll see data plane impact. We also have this external service that helps us out during a warm upgrade while the control plane is down. And this helps us service the ARP-enabled discovery packets so that the nodes connected below the TOR, they are able to get the MAC addresses essentially. And the last thing is we need to make sure that the migration from the old version to the new version has safe and consistent state. And that's what I'm going to focus on today. Before I go there, I need to define this concept called data consistency. Now, this is the key indicator of how successful a data migration was. When this is 100% consistent, this is the goal state. For a constant set of config files, a warm upgrade to version B has data consistency with a cold boot to version B. And also within that running device, the data stores, whether that be ASIC DB, state DB, the data contained in those, it's consistent across the two. Any less than 100% consistent, this is called a difference. And the larger the mismatch with this, the greater the difference. And when there is a larger difference, the riskier the warm upgrade will be. I've grouped these into two categories. We've got checks between the software and hardware, as well as checks between software from a warm booted state and software from a cold booted state. And you can visualize all these checks in a matrix like this. At the moment though, we've only got a partial implementation of these four here. Now here is a visual representation of what can happen with these differences. So in this middle row here, we've got cold upgrades from version A to B to C. This is our most tested path from our Sonic management test suite. But if you look at this top path here, where we start on version A but then do a warm upgrade, you can see there's a slight difference there between warm booted B and cold booted B. And then if we take another warm upgrade to version C, the difference grows and it's different again. And an alternative path was we start on B, do a warm upgrade to version C, and there's another difference again. We don't know what these differences are at the moment, but you can almost guarantee that there is one there, and that's a risk. But now with these 4 checks we have, we've found some differences, we've fixed them, and our differences have shrunk. And now the warm upgrade is a little bit less risky for impact to the data plane. But the dream state is to do all of these checks, find and fix all the problems, and then it doesn't matter if we do a cold upgrade or a warm upgrade to our next version, they'll be consistent. And so a cold reboot will equal a warm reboot. And therefore, our large Sonic management test suite that tests the feature set of Sonic from a cold booted state, that is directly applicable to the warm boot upgrade as well. So we get a lot more confidence there. Now going back to those two groups of checks that I said before. The first one, hardware versus software. How do we do this? The first thing we do is we take a dump of the ASIC DB from the Sonic OS, and then for each SAI object that doesn't have null values, meaning it's not a placeholder value, we then do these SAI get calls via PySci Redis and the Redis notification channel and compare the result that we get there. And these are the kind of results that we get. We get about 16,000 results after we exclude the empty placeholder values, but we're only getting about 2,400 values matching, which is only about 15%. Of these other 85%, there's actually a large majority with different kind of keys. So this is just, we haven't implemented this yet. And then also, even though we have these values in our ASIC DB and we go to do a SAI get call, we're getting a not implemented result back from our SAI layer. That accounted for a few more. And then a larger group was we were getting buffer overflows in the C library as well. The goal is to cover these other cases, but until then we've constrained the set and we're only looking at 5 objects for the moment. So we're looking for all attributes for pools, profiles, switches, and WRED. This last one, port, we're not actually looking for all values. It's all except for 2. And the reason we're not looking for 2 of them is because we found on a particular version that if we do a SAI get call, it had a side effect of setting the speed of a port, and that was causing data plane impact. So we've excluded that. So there's actually another column in here that I haven't put, but it's the number of values after filtering out the ones we're not interested in. So when we look at that, the result set's much more clean. The other group of checks is software cold boot versus software warm boot. With this style of check, what we do is we take a snapshot of the application DB, config DB, and state DB after we've done a warm upgrade. Then we do a cold reboot and take another snapshot, and then we start comparing the two. And this is what we find with config DB. It's a perfect match. I'd be very surprised if it wasn't a perfect match, as after you have warm booted a device, we have this process called warm boot finalizer, which saves the running config to disk, and when you cold boot, it reloads that from disk. So it'd be very concerning if there wasn't a match there. More interesting though is the state DB. In here, you can see there's quite a difference between the warm booted values and the cold booted values. The count of them, that is. There's about 574 different. There's some expected differences though between warm boot and cold boot. In the warm booted scenario, we do store information about how many times our processes have gone through a warm reboot, and we don't expect to see that at all in cold boot. So we need to filter that kind of thing out. There's also about half the database really is their volatile values, like temperature and CPU and memory, and they're never going to match. So we need to filter those ones out too. But of the differences here that we're seeing, it was quite common to see that one version or the results after one upgrade, say warm boot, they would have a value like n/a, not applicable. And then the cold booted values, they just wouldn't be there. So there's different representations of the same state, which we need to clean up. Application DB, similar problems there. Yeah, it's more of the same really. So where all of this work has come from is basically what we've been seeing in production. When we have data plane impact, this is the categories or the causes of those impact. You can see half of it is from software to software inconsistencies, and then 30% from software and hardware. So if we can close all of those comparison checks in the matrix I presented earlier, then I think we can put a really big dent in these data plane impacting issues. Some resources from what I've spoken about today. These slides will be available afterwards, so you can click through to those. And I need to thank the team around this work. These ideas are from the team. We've got Vaibhav, Sai Krishna, Ying, Ryan, and Dawi. And if anything I've spoken about today sounds interesting, or Sonic in general sounds interesting, head to sonicfoundation.dev, where you can contribute on test infrastructure, use cases, OS features, or anything like that. Thank you.
Thank you, Ryan. Folks, any questions, please line up and ask.
Hi, Ryan. Thank you for that presentation. I'm Rohit from Nokia.
Yeah.
I had a question about ARP-ND that you were referring to earlier. You had timers referencing LACP and BGP as to how quickly you want the control plane backup. For ARP-ND, you mentioned there's an agent or something like an agent that runs. Is there a timer associated with that you need the system to be back up within that time window so that the servers don't time out their IPv6 peerings?
No. Basically, the control plane assistant server that's set up on demand by the device when it does its warm reboot. So it sets it up when it needs to, and then when it's coming up in the new version, it will tear it down when it's ready to tear it down. So the life cycle of that is driven by the device itself. That one's quite a flexible part of the whole warm upgrade process.
Okay, thank you.
I'll ask a question.
Yeah.
Could you share some examples of the software-to-software inconsistency or the software-to-hardware inconsistencies you talk about, and maybe some insights into what may have caused those?
Yeah. I'll start with a software-to-hardware inconsistency. We've seen an issue before where you'll start on version A, you'll do a warm reboot to version B, and somewhere down in the SAI layer, the ECN config value has switched from all to none, but there hasn't been any data plane impact at this stage. But then when you go to take one more warm upgrade to another version, that value flip seems to get programmed into the hardware itself. And so now the ECN marking has been removed, and it starts to cause data plane impact. And then for a software-to-software issue, it's similar again. You'll start on version A, do a warm upgrade to version B, everything's fine. It appears to be fine, no data plane impact. But our ASIC DB has discovered some extra objects that are just lying there until you go and do one more warm upgrade to version C. And in there, when we're booting up in the new version, SyncD has decided that these objects that we found previously they're no longer needed, and it attempts to delete them. But it gets met with site object in use. And to recover from that scenario, it crashes and cold starts itself, which causes data plane impact.
I see. And were these attributed to just bugs in SAI or in SyncD?
It's a mixed bag. Sometimes it's SyncD, sometimes it's SAI. And it's also the history of the device, how many warm upgrades it's gone through, that brings about these bugs too. And it can also make it hard to say what part of the system is truly at fault as well. So we've got to handle it on a case-by-case basis. Yeah.
Well, may I have one more question? Did you have a chance to check if warm reboot is consistent also across different devices? Like if you take device A and warm boot it to one release, and then you take device B, warm boot it to the same release, do you run any checks across those?
No.
Like the consistency of the warm boot itself?
No checks between devices.
Okay.
It's always the same device in its intended topology under different upgrade paths, upgrade histories. Yeah.
Thank you.
Yeah, I don't see any other question. Thanks a lot, Ryan. It was really informative. Thank you.
Thank you.